let's see, I think we're about ready. Let's begin. Okay. Let me do my standard thing. Okay. I've also put up the notes from Tuesday. So I think one thing that we need to do before we can have a next exam, so in terms of some questions on Discord about the next exam, the first thing we need to do is have a homework 4, and I'll try to write that tonight. And so maybe it'll be due maybe next Thursday or something like that. Basically, it's going to be, we're going to start from AVL trees, and it'll cover up to, say, red-black trees. It won't probably not cover Heaps. We'll put that on homework 5, and then we'll need to talk about the second exam. And that's really all I have for announcements, is that I'm planning on doing it. Hopefully everybody's been doing well on Project 3. Because Project 3, in my opinion, of course, is probably the easiest so far. And of course, but I mean, maybe I'm totally wrong about that. I think that if you've started already, you have a good chance of making progress. Let's see here. Let's look at the project itself. Okay, that's Project 4, which hasn't been released. Okay. So, I guess the other thing I'll say is that if you haven't made significant progress on it yet, you should probably try to do so. And if you're having any problems, you can always talk to me. I can possibly help over the weekend. And on, I guess, when is the project due? It's going to be due on next Tuesday. So, yeah, so if anyone has any problems with the project or you're having major difficulties, you can always try to get some help from me so that you're not running into the last day. I want everybody to be able to finish this thing with time to spare, It would be I guess it would be a perfect universe, right? If nobody was working on this project on Tuesday, everyone had finished. So that's my perfect universe, is that everybody's done on Monday and you're just, doing stuff. Okay. Okay. All right. So, yeah, talk to me about the project if you have anything. I think it's basically a straight up skew heap, right? I don't think there's anything terribly, what should I say, terribly imaginative about the project, in the sense that it's not a Discord tree, it's not something that's new and been invented specifically for the project. It's a straight up skew heap, right? So I think that my skew heap lectures should have most of the information. Okay, so let's get back to array-based heaps. Yeah, so Project 3 is the easiest so far, but that means get it done, ask for help, get hundreds. Okay, that's what it means. All right. So, okay, let's get back to array-based heaps. Besides skew heaps, will the other heaps be applied to homeworks and exams? Of course, yes. Yes, of course. You're probably going to see more leftist heaps on the homework, since you're seeing the skew heap on your project. So, yeah, the things that I'm talking about that don't get made into the project probably get made into your homework. So, okay, so let's talk about array-based heaps a little bit. And then maybe we'll talk a little bit about binomial heaps. And I know I wrote binary as the title of this file, but let's make an array. And just, I mean, I know that I did all this last time, but the rule in life is that you can never really repeat stuff too much. Well, I guess you can, but the rule in education is that you can never really repeat stuff too much. Because, as it turns out, maybe people didn't completely understand it the first time. And so if this is index 0, normally we block off index 0, and the reason why we do that, so let me explain why we do this. Why do we block index 0? And the answer is because if we do, then each node, so if you say the left child of x is just equal to 2x, and the right child of x is at index 2x plus 1. If we don't index 0, then the children of 0 are 1 and 2, right? This is the left, which is 1, and the right, which is 2. And so you have to think about what the formula is. And unfortunately, the formula gets modified a little bit. So there's a number of ways to express the formula, but basically the left child, the modified left child, if we start off at 0, has to be equal to 1. So just multiplying by 2 doesn't work. And also here, the right child mod of 0 doesn't work either, right? So we would have to make that 2. So basically what you have to do is you have to come up with some formula that works. And of course, it doesn't just have to work for 0, 1, and 2. It has to work for all of them. So let's see what it is. So I think, let me see if I can modify it on the spot. So the left child of x is going to be equal to something like 2, and then it's going to, I forget, is it like 2, probably something like x plus 1 minus 1, or something like that. And then this one is going to be, the right child is going to be, I'm sorry, 2x plus 1, like that. So let's see if these formulas are correct. So of course you can say, well, we can simplify this one into 2x plus 2 minus 1, which is 2x plus 1, like this. And this is equal to 2x plus 2. So maybe this is actually not so bad. It's just everything is shifted off by 1. But let's verify that this is correct if we don't actually block off 0. So if we don't block off 0, the child of 0 is 1 and 2, right? So 0 plus 1, so that's 1, so that works. And then here, 0 plus 2, that works. So now what's the children of 1? So the children of 1 are at 3 and 4. So 2 times 1 plus 1 is 3. 2 times 1 is 2 plus 2, that gets you to 4. And then hopefully it'll work for 5 and 6, and that's basically where I'm going to stop. But the point is that we'll just, technically, if you wanted to prove this, you might have to do some kind of, induction argument or something like that. And but the point is that the children of 2 are 5 and 6. So 2 times 2 is 4 plus 1, that gets you to 5. 2 times 2 is 4 plus 2 gets us to 6. So, you might say, well, you haven't proved it for all x, and I agree that I haven't proved it for all x, but I've proved it up till 6, and so it's a pretty good kind of hint that this actually does work. But the point is, if you don't block 0, then you have to come up with slightly altered, slightly shifted formulas so that everything works out properly, which is, as you can possibly guess, it's a little bit annoying. So traditionally, they just block off 0 because now you have that the left child is just at 2x and the right child's at 2x plus 1. So basically, whatever is at the index here, right, this is root equals 1. And then here's index, let's copy paste the rest of the indices, right? 2 through 6, and then maybe we'll add some more in just a second if we need anything. So the root value here is, say, 54, right? And now 54, as it turns out, is going to have to be the largest element, or technically the smallest, but let's pretend that this is a max heap. So if this is a max heap, then the root has to be the largest element, and 2 and 3 have to be smaller than it. So like, say, 34 and 45, those are both fine. And then 4, right, so 34 has the children 4 and 5. So this element would invalidate, right? So this means it's not in an array heap anymore. And the reason why is even though, right, 45 is bigger than 41, the answer is actually that what? The left child of 2 is equal to 4. The left child of 3 is actually what? 6. So there's no, basically what I'm, yeah, there's no connection between 45 and 41. It's only 2 and 4. So this one's no good. So let's make this 31 instead. And so this is the right child, so it has to be, say, maybe 5. And then the child of 45 is 6 and 7. So this one can be 41, and this one can be 39, right? And so if we were to draw this as a tree, then what we would actually see is something like this, right? We would see something like that. Okay, and so remember what we have to do in order to, please don't crash. Are you gonna crash or you're not gonna crash? You haven't crashed in a day or so, so I think you might crash. Yes, called it. Wonderful. Almost got it back. Thankfully, I did save. All right. Sorry about that. Okay, so basically, now let's just go over quickly the methods that we're going to use to delete and to insert, right? How do you insert? And the answer is, from the array perspective, it's actually really easy, right? From the array perspective, all you have to do is stick the thing in at the last index into the array. So here what you're going to do is you're going to say, if I'm going to insert, say, 51, right? You just stick it on there as in slot 8. And let's actually number these slots. So here's slot 7, and here's slot 8. And so the point is that if you stick this on in slot 8, the idea here is that it's in the wrong position, right? It's in the wrong position because if you stick something in slot 8, it is the child of 4, and 4 is 31, so here it is. So basically, this is where the thing is going, right? So this is how you insert. First step is you stick it onto the end of the array. Stick it onto the end of the array, right? But I don't really mean the end of the array. What I mean is like the current value. The array can be as long as you, not as long as you want, but it can be some fixed length that's larger than the heap. Okay, cool. And now, what we're going to do is we're going to do the percolate up process, right? So what's the percolate up process? The percolate up process is the process where you do something like this. So you say, okay, 31 and 51, they don't match, so we're going to flip this one up here. So now 31 and 51 are going to flip. And so you do that by looking at the element at n over 2, right? Because n over 2 is always the parent. Okay, cool. And then you look, well, what is 4 divided by 2? 4 divided by 2 is 2. And so you look up and the parent is 34. Do you have to swap? Yep. And there you go. Right? So that's how you insert, is you stick it onto the end of the array and you percolate up. And you percolate up by looking at the element at position x and x over 2. And of course, you should always understand that I mean int of x over 2, right? Because technically you could end up with a fraction, but who cares, right? Because if you divide 7 by 2, you're going to get 3.5, but you know that the parent of 6 and 7 are both 3, right? And so the only the distinction here, and so you might ask, what happens if we don't do the 0 indexing? And this is where the actual problem comes in, if you notice, because if you divide by 2 here, the parent here would be, it would claim x plus 1, but if you divide here, it would just claim x, because this extra plus 1 would get basically ignored by the integer calculation, so we would just end up with x here, But this is actually, right, this is literally, you can factor the 2 out, so it's 2 times x plus 1. So the point is that if it's an even one, you have to subtract 1 and then divide, and if it's odd, then you can just divide, and that's how the parent works in this process. So again, it's that's why we kind of ignored the 0, because it just makes it more convenient. But yeah, if you don't ignore 0, you have to mess with these calculations. It's like int of x minus 1 divided by 2 or something like that. Actually, yeah, int of, if you use the 0 index, you have to do int of x minus 1 divided by 2. And so it's just a little different. So insertion is pretty easy, right? Insertion is pretty easy. So if I just inserted, well, like what if I insert 22 here? If I just insert 22 here, it's just going to go straight into the tree. And you notice that 22 is less than 34, so it's happy there, right? It's not going to do anything. Right? It doesn't need to be percolated up. It's the right child of 34, not the left child of 5. Okay. Now the question is, how do you delete? And let's go over that. So how would you remove the max from the heap? And so in this case, and I should say maybe I'll talk about that in just a second, how it's different from a skew heap, because I think I didn't exactly mention it last time, and I kind of want to. So the process here is you move it up to the top, or move what up to the top? Move the last element up to the top, right? And so what you're going to do is you're going to pop off 54, so 54 comes out, 22 goes up, right? And 22 is great because 22 is saying, hey, I'm 22. So now remember, you cannot just pick at random, right? So what does the percolate down process do? Percolate down process, right? You can't just percolate down to the right or the left. What you have to do is you have to percolate down in the direction of the biggest child, right? And so what I mean by that is that when you percolate down, you say 22 is less than 51, 22 is less than 45. You have to pick the biggest one here. So 51 is bigger than 45, and so you'll swap this way, right? And the reason why you're going to do that is because if you think about it, if you did it the other way, right? If you did it this way, then we actually get the problem, right? Here is happy. The right child is happy. Things are in the right order. This is still messed up, but we can fix that. This way, though, is still bad, right? But we thought we fixed it. If you don't pick the biggest one, it's possible that a bigger thing is sitting here, and if you don't flip it up, then this will still not be an array heap, or any kind of heap. So that's why you always have to pick the biggest child to get percolated. Okay, whoops. What the heck did I click? There we go, that's what I meant to click. So, okay, cool. And now here we see 34 and 5, and so we'll flip these, right? Flip those. And then finally, we'll flip here, right? So you flip in the direction of the maximum, right? And so in this case, what actually happens in the array, let's look at what happens in the array, because that's also important. So here's where the array starts out as. We delete this out of the array, so this becomes, say, the maximum. We put this in here, and then we say, okay, oh, this is actually different. Is this a different array heap? I think I haven't. Or did I just not finish? Oh, I just didn't finish. This is what it has to be, right? There we go. Now that that's done, we can fix this. There we are. And so now that we fixed that, now we can actually do what we wanted to do. We pull off the 54, put the 22 up, and then you say 22's children are 2 and 3, so I'll swap it like this. And then 2's children are 4 and 5. Pick the biggest one. And then 4's children are 8 and 9. But 9 doesn't exist currently. All we got is 8. So we do this. and we are done. And so now you see if you reconstructed the heap from the array, we would get the same tree structure. Okay, let me say one thing about an array-based heap versus, say, leftist and skew heaps. Okay, so basically, when you do a merge, right, in a leftist heap or a skew heap, it's O of log n, right, in the size of the... Or I guess you could say when you're merging two heaps, it's like really 2n or something like that, but who cares, right? So I promise you that the constant, like the log of 2n is equal to the log lg of 2 plus the lg of n, and the log base 2 of 2 is equal to 1, and so basically it's 1 plus log of n, so that's lower order terms, so big O will ignore it anyway. But the point here is that, what is the point? The point is that an array-based heap is not a very good mergeable heap. So what are the advantages of an array-based heap? Well, it's an array. So you don't have extra pointers, right? You don't have a null path length calculation. Basically, all you have are data, and you have the size of the... You have, two things in your class. You have the size of the array, and you have the current size of the heap, right? So that's like 2 integers plus an array of data. So almost no additional stuff. You don't have a bunch of pointers to nodes that contain the data. It's all just contained in the array. So that's nice. That's great. So that's an advantage for, and what's another advantage? Well, insert and remove are both O of log n. And we've guaranteed that, and the reason why we've guaranteed that is, the proof of that is that the tree structure is always, it's not always perfect, but it's always complete, which means that it's essentially perfect plus some extra stuff on the lowest line, right, from left to right. And so what complete means is that the tree is perfect except on the last row, and in the last row it has nodes from left to right. And so being complete is almost like being perfect, and it's very close. It's very close in terms of in terms of its runtime. And the reason why is because, remember, the one thing that we know is that a perfect binary tree, not even a search tree, not just search trees, has, right, 2 to the h minus 1 nodes, right? And so the point is that if you have 2 to the h minus 1 nodes, and 2 to the h minus 1 is equal to n, and you know that the scanning time for any of our algorithms, percolate up or percolate down, are O of h, right? Because insert and delete are both O of h, because basically what do? You just go down the tree or up the tree, right? So you never go back, you never backtrack, you never go down 2 different paths. So you're always just O of h, which is great. And now you know that if you scan, right, if you solve, you get, m plus 1 is equal to 2 to the h, and then you get log of n plus 1 is h. So actually our algorithms always run in log of n plus 1, which we generally ignore the extra plus 1 bit and just simplify it to log of n. So that's a pretty compelling argument for why this is all O of log n. But then you would say, what are the advantages of a leftist heap? I always do that, LFT, IST, or skew heap. And so the answer is that we expect, right, that the runtime for both are about O of log n for insert, delete, because both of them are based on merge, right, and merge is O of log n. But there's an extra operation that you can do with one of these heaps, and you can merge not just the heap with itself in like a deletion operation. You can merge with a completely different heap, right? So if you have one heap of size n and one heap of size, say, let's say make one heap size A and one heap size B. Normally I would say N and M, but nasal consonants are stupid, so and hard to distinguish between. So I'm just going to call it A and B. We can distinguish pretty easily between those two letters. So the idea here is that if we're going to merge with a completely different heap, we know that essentially what's going to happen is the biggest we can ever have is, say n is equal to the max of A and B, the most expected time we're going to take, and it's not perfect because you could always construct, there are ways to get leftist heaps to have an O of n operation, but basically on average, the expected runtime for a leftist heap or skew heap for a merge would just be O of n. I'm sorry, O of log n. But if we think about it, what would the time... okay, I think I need a new text block because it starts to get slow. What would be the expected time for an array-based heap? And that's a good question. So if you had two heaps, right, two array-based heaps, how would you merge them? So let's pick on this guy. Let's take it. And then let's pick on another one. Let's make up a new one. And how would you merge these two things? Well, as it turns out, it's a little bit hard. And so here's the reason why it's hard. Because let's say we do something like 24, 13, 7, 5. Let's make this 11 and 9. Let's make this 5 and 4. And then this is the child of 11, so we can make this 7 again. Okay, so if you're going to merge these two things, it's a little bit hard to see how you're going to do it, right? Because, I mean, one idea, the simplest idea, would be to take this array, right, and to sort of just copy it here, right? Now, that's an idea. You could do that. But here's the problem, right? If you do this, you're messing up all the children, right? Because then you would be saying that, like, what happens if we do this, right? This is slot 9, so that's a child of this. So actually, this would more or less be okay, except, so this is slot 10, slot 11 and 12, so that's the child of, or no, hang on, 9 and 10, 11 and 12, so these are the children of 4, these are the children of 5. I should just write it all in so that I'm not as confused. So 9, 10, 11, 12, 13, 14, 15, 16. But here's the problem, right? Here's the main problem. Who were the children, right? Who were the children of this guy, right? The children of 24 were 13 and 7, but now 24 has children, or 18 and 19, which don't even exist. So none of these actually have any children. They're all children of these ones. We don't necessarily know. So this way, it's good, right? If we insert it in this orientation. But what if we inserted it in the other orientation? What if we merged it the other way, where instead of going that way, we actually merged it more like this, where this one was all at the front, and then this one was at the back, right? Then it's the same thing. All the nodes have the same numbering, except now what do we see? We see that, like, the children of, say, 5 are 10 and 11, but they're both violating the property. The children of 6 are 12 and 13. This one violates. 7, this one, they both violate. And the children of 8, 16 and technically 17, which doesn't exist here, but whatever, it's just a one-child thing, it also violates. So the point is that, and then of course, even here where you say the children of 4 are, 8 and 9, right? But 9 was the old root, and so the issue here is that you would have to do a complete reconstruction of this data structure, right? You'd have to do a complete reconstruction because potentially all the new nodes that you inserted would be in violation of the heap property, right? That's the issue here, is that you'd have to basically completely rebuild the whole thing. And of course, that's going to take you something like n log n time, right? Because you're going to have to reinsert n objects into a data structure, each of which takes log n time. So the total reconstruction time is O of n log n, right? And so that is the total reconstruction time, which means that merge for an array heap takes literally n times the amount of time that it takes for a leftist merge, right? So it is significantly worse, right? That's the point here. And so array-based heaps have a lot of advantages. They're definitely more space compact. There's some good things about them, right? I'm not saying that they're terrible. But if you need a merge operation, right, then there's a reason to use leftist or skew heaps, right? That's the reason. That's the exact reason that you would use a leftist or a skew heap, is precisely if you need the merge operation. If you don't need merge and you're happy with insert and delete, which a lot of times that's all you need, right? So most of the time in your life, you're not going to really need the merge operation. But basically, the merge operation is useful if you had, let's say that you had, here's an example, right, in real life. Let's say that there is a call system where people's calls are determined, the priority of their calls are determined, or is determined, or yeah, the priority is determined by some keys they hit, right? So they call up the system and it asks them a bunch of questions. It says, I don't know, if it's, let's say it's a bank software or something like that. It's like, are you currently experiencing an emergency where you need the bank immediately to like cancel your credit card? Have you just been robbed? Or alternatively, it's like, do you just want to check your balance? And let's say that you can't do that automatically or whatever. So the priority of someone's calls are determined by some formula based on responses, right? And the idea here is going to be that, let's say that you have a call center, right? And so a number of calls are going to be determined. So each person at the call center gets their own heap, right? And then, of course, what you could say is, what if person X gets off shift and goes home, right? Then what you could do is, this is one reason why you might be able to use merge, is that you would merge person X's waiting calls, right, with, say, person Y's waiting calls, and that way you could merge two things together. You could also talk about it in terms of processors, like if you have a whole bunch of processors that have to process a certain set of data, and each of the sub-processes, each of the programs that's running on each of the processors is determined, but then one of the processors goes offline for whatever reason, and you have to redistribute the work. So basically, the merge process is always good when you have to redistribute the work redistribute the work is basically what I mean. Okay, so I think that's a decent example of where you might want to do some kind of merging operation. But if your array heap is not doing anything like that, then there's no point to have a leftist heap or a skew heap, right? You can just do an array-based heap, and it's going to give you probably just as good runtime, right? Probably better runtime. The only time when you need the leftist or the skew heap kind of stuff is when you need to do a merge. Okay, and then the last thing that I'm not sure if I'm actually going to code it or not, but the last thing to say is remember that the underlying data structure here is really stored as an array. So it's always possible that you'll try to insert and the array will just be full. So if the array is full, one way to kind of fix that is that you can do what the vector class does, right? The standard std vector class. And of course your question is, well, what does std vector do? What they do is when you reach the end of whatever they've predefined, like say you have a vector of 100 elements, and say you try to, you push back the 101st element, then what ends up happening is they create a new structure with 2 times 100 elements, or 2 times whatever the number of current elements is, and then what they do is they copy the old into the new, and then they delete the old and set the pointers. So that is one thing you can do. The only problem with this is, and this is another disadvantage, is that this is an O of n operation. So most of the inserts are going to run with a log n, right? For most inserts. But kind of randomly, you'll get an O of n insert, right? And you can avoid this by doing more complicated things, but if you just do it this kind of more basic way, then you're going to end up with a random O of n insert. And it's not really a random O of n insert, though. Like, the one thing to say about it is that it occurs, when does it occur? It occurs right when we hit the maximum number of elements. So if we hit the maximum number of elements, then we have to do this operation. So we're going to hit this thing, what? Like, if you have an array of size n, or if you want to insert n objects, and the max size was m, which let's say is less than n, then the point is what you need to find is you need to find the value of 2 to the k times m, which is bigger than n, and then it will happen k times. Right? This reconstruction will happen k times. And so the point is that if it happens k times, then you'll have n, you can solve for k by doing, it's the log of n divided by m, right? K is equal to the log of n divided by m. And so since that's the case, the last thing to say about this is it will only run this like once every, very rarely, once very, every few, it's hard to even describe how it's going to run it like once, and then it will run it once after 2 times that many insertions, then 4 times that many insertions, then 8 times, then 16 times, etc. So it's going to, I guess I'll just say it'll only run this very rarely. So the point is that overall, it doesn't actually affect the expected runtime, but it does cause these runtime spikes. So the only problem with this kind of data structure would be if you had an array. So if n was equal to, say, 10 trillion, right? This would be the problem, because if you set m equal to, say, 100 million, then you'll end up running this thing a number of times, and the problem is that every time you do an operation on 10 trillion things, it's going to slow you down. The reconstruction might take hours, right? So the regular operations will take microseconds. But randomly, you'll hit an insert that takes like 6 hours, right? And that's no good, right? So actually, a leftist heap and a skew heap won't suffer from this problem. But there's also other ways to solve this problem that don't just involve going to a different data structure. You can just make the array kind of chain like a linked list, or do some other... There's other ways to solve this. There's more creative ways that'll hammer down these spikes, right? And of course, you wouldn't necessarily be expecting it. So what ended up happening is you're sitting there with your program, and you're inserting elements, you're inserting elements, you're inserting elements, and all of a sudden it's just like you insert one element, and boom, it just starts. The progress bar comes up and it says expected time to completion 2 years, right? So, so that's going to be an issue. Anyway, so that's basically the point here, right? Is that the underlying data structure is really stored as an array. There's a bunch of problems that creates, and there's a bunch of ways to solve those problems. I'm not really going to go into it. I'm just going to say that there are definitely ways around these problems. You don't, if you are actually building something that's going to run on a, like, and you know that there's going to be 10 trillion entries into this thing, then you're going to be like, wait, we need to fix some of these problems. If there's only, say, 10,000 elements ever in this heap, then you never have to care about any of this stuff. So only ever when your number of elements in the thing gets so large that you have to really start to worry about this. But that's the whole point of Big O. Big O worries about what happens as n gets really large, as n goes to infinity, right? It worries about the cases where, like Big O computations always worry about the cases where n gets as large as possible. Okay, so I think that's all I really want to say about array-based heaps, and I'm glad that we had the chance to talk about it all again. So now let's get into my favorite topic. You know what? Maybe I'll even just start a new document. Should I start a new document? Yes. Yes, I should. And there's a reason why I need to start a new document. It's because we are going to talk about not binary heaps. So what we're going to talk about is binomial heaps. And so binomial heaps are a pretty fun data structure. Not very useful, but I do love to talk about them. And the reason why I love to talk about them is this. And let's get straight into it, okay? Now, I want you to forget everything you know about heaps, because we're not really going to be talking about heaps for a little bit. What we're going to be doing is we're going to be talking about random circles. So I'm going to call this circle B0. Now, normally it's a subscript. Maybe I'll even make it a subscript. Let's do a subscript, because I want to do it right. Okay, let's hit it. And of course, it's going to take a long time since it's the first time that LaTeX runs. It always has to pull it up and get it running. And there we are. Okay, now let me move this off screen. Then it should be over here somewhere. Don't get seasick. Sorry about that. I hate when it does that. Okay, where the heck did I move it? Where'd it go? All right, let's try it again. There it is. Cool. So this is what we're going to call a B0. All right. Cool. So at this point, you're like, I'm totally bored. I'm uninterested. I don't care. You've just drawn a node and called it B0. All right, I understand. Don't worry. It's going to get interesting in just a second. So let me construct a B1 for you. So here's the rule. To construct Bn from Bn minus 1, what we're going to do is we are going to take two Bn minus 1s and then add a Bn minus 1 as the child, I guess as the leftmost child of the other Bn minus 1. So I'll show you what I mean by this. So it might not be completely obvious what this means until I do the first few examples. So I think this is probably the best way of saying it. So what we're going to do is this. This is the construction of the B1, and here it is. you take two of them, and you kind of merge them together this way, where one of the B0s becomes a child of the other B0. So this is what we're going to call a B1. And let me put in a B1, and then I'd better, here it is. Here's B1. Okay, so now we have a B0 and we have a B1. Okay, so how do we make a B2? Right? I want this to be straighter because unfortunately, you know what, actually that is totally possible. There, we can do that. Then we take from the center point here. I don't know why it's trying to track there. There we go. Let me save this before it crashes again or something like that. So, whoops. Don't know why it defaulted to the grading folder. Let's see. What am I doing? There we go. Okay, so now let's make a B2. So how do we make a B2? We make a B2 by taking two B1s. Let me delete the B0 out of here because now you're pretty convinced. So this is a B1, and this is a B1. So we're going to do it like this. We're going to draw it in like this, and you might be confused about why, but you'll just have to go with it. And then we add this one as the leftmost child of the other one. And so now this is what we will call a B2. And so, you know, as you might guess, the next thing we're going to do is make a B3, and then a B4, and then a B5, etc., etc. So, all right, here we go. Let's see, can I get rid of this line? Yes, I can. Okay, so that's a B2. So then your question is, how do I make a B3? Well, what I do is I take two copies of B2. I'll delete all the B1s because we get it. Make two copies of B2. One like this, and one like this. And then we join them together like this. And so this would be called a B3. And if I will get to a heap eventually. We're going to make a heap out of all of these things. But not yet. I just want to do 4 and 5, and then we will make a heap out of it. Okay. So this is a B0. A B0 is just one node. A B1 is two nodes like this. A B2 is four nodes like this. A B3 is like this. Let's make a B4, because why not? So B4, it's going to be big, right? It's going to be big because, is this a B4? No, this is the B. This is B4. Yes. So again, let me delete B2s because we get it at this point. So this is a B3. This is a, whoops, come here, a little B3. All right. And now this is going to be a B4 structure. And maybe we'll just do one more for the sake of ridiculousness, and then we will make, crap, I didn't, I hate when I can rotate. I almost wish I could turn off the rotation feature. So, there we go. And one more just for safe measure, right? So we're going to make a B4, right? Let's make two, so we have to take two B4s to make a B5. And we don't match them up like this, we match them up like this. And the reason is because this one, this B4 becomes the leftmost child of this B4. And then this is the end. So BNs exist much higher than 4. You can keep making them. But I'm going to stop at 5, like this. And the reason I'm going to do that is just because I think that at this point, the picture is what it is. Okay. There we go. All right, and now your question should be, all right, you have done all of this, right? You've made me sit through this construction where you've copied and pasted all kinds of things together, and you're like, but none of this makes a heap, right? And I agree, none of this makes a heap. It is not a heap right now. There's nothing heapish about it. You might be like, I see some kind of tree structure going on here, but I don't understand how you're going to get a heap out of this. And so, or maybe you can kind of think like, oh, you're going to do something crazy and get a heap out of it, which I'm about to do. But the point is that a true logician would look at this and be like, cool, you've constructed this thing. What was the point? Here's the point. Here's the point. We can make a heap out of this by doing this. The heap construction using the BNs. What we're going to do, and let's just talk about, there's another merge algorithm. Everything is merge, right? So insert is going to be merge, and then delete is also going to be merge. So let me talk about what merge does. Well, yeah, let me talk about insert and merge together at first. But everything is really merge. So let's talk about how you insert. So what you do is basically the rule is going to be that you can only have, stop rotating, you can only have one BI of any given type. So let me just do an example. Let's insert into an empty binomial heap, which of course you don't really know what a binomial heap is, so you don't really know what an empty one is, but we're going to insert, say, 5 into an empty heap. And so here's the node. Now there's no B0, so we're going to make it into a B0. Okay, now let's keep doing. Now let's say that we're going to insert, say, 8. Okay? All right, so if we insert 8 into a binomial heap, then here's the thing. This was a B0, and this is a B0, right? And so that is against the rules. So the only rule I've told you so far is you're only allowed to have one BI of any type at a time, right? So let's write that down as a rule. So the rule, you can only have one BI of any I at a time. And here you say, well, you've directly contradicted yourself. Now you have two B0s. Well, guess what I can do with two B0s, right? What can I do with two B0s? I can make them into a B1. So that's exactly what you do. What you do is you take these two B0s and you make them into a B1 like this. You say, who's the biggest? 8's the biggest? Okay, you go on top. You go on the bottom, right? And now you see, as simple as this is, we have a heap, right? Cool. And you might say, now this is a B1. Right, B1. So now if we insert another element, let's say we insert, say, let's insert 14, okay? Let's insert the number 14. Now you might be tempted to say, well, 14 is bigger than 8, so. The answer is, actually, we don't have to do that yet. And the reason why is because, let me actually just get a whole bunch of B1, B2, B3 business. Cool. So here we have a B1, right? And if we're inserting into this thing, we notice a simple fact. The simple fact is that we haven't violated the rule, right? 14 is in a B0, this thing is in a B1, we're good. All we have to do is just kind of rearrange them so that the B0 is in this slot and the B1 is over here. And so this is a completely legal, and ignore all this extra crap, I'll just put it down here so it's not visible. This is a completely legal binomial heap. Okay, so now let's insert another element. Let's insert, say, 7, right? So we're going to do it again. We'll insert 7. So now what we do is we merge, right? You can see how this is kind of like a merge. What we're going to do is merge the 7 with this, at which point you say, uh-oh, there's a problem, right? You ask, what's the problem? The problem is we have two B0s. So if we have two B0s, we have to make a B1 out of it. So how do we do that? What we're going to do is we're going to take this one and merge it into here. or I guess I should say make it the child of 14. And at which point you'll say, uh-oh, you fixed one problem, but you've created another problem, right? We fixed the B0 problem, but we created a problem with B1. But then I say, but you know what to do, right? It's the only thing we know how to do with the BIs, right? These little binomial trees, right? What is the only thing you know how to do with them? Well, you know how to take them and to make them into a BI plus 1. So what you get to do here is you basically get to say, who's biggest? 14 is biggest? All right. So we'll take 14 and put it at the top, and we'll take this B1 and we'll make it the right child or left child like this, and join it up. And then we mark it as B2. Like so. Cool. All right, so we're done now, right? Because there's only one BI. And as you see, this thing is now a heap, right? It's a heap because this is the largest, and all the way down they're smaller. And you notice that we can always do this kind of merging operation, because at every point where we do the merge, we ask which of these two are bigger, and then we just stick the rest of this on as a child, and so that's okay, right? There's no problem here, because we know all of the children of 8 are less than or equal to 8, and therefore less than or equal to 14. Okay. So now let's do a bunch of more insertions. Let's say that we insert a whole bunch of extra stuff, right? So let's copy paste until we have, so here's a B1, let's copy a B0. Let's say that we somehow get to this state, right? So we're at the state where we have, this is our data structure. Now let's change some of the numbers. Let's move all this out of the way. Okay. So here's our data structure. Let's say that this is equal to 16. Sure. Let's make this equal to 4. Let's make this equal to 12. All right. And now what we'll do is we're going to do another insertion, right? So here, this is the state of the data structure, right? This is the state of the binomial heap before the next insertion, right? And so what we're going to do, of course, is we will insert again, right? And now let's insert, say, what should we insert? I don't know. Pick a number, any number. Let's pick 9. It really doesn't, I mean, it does matter, of course. I shouldn't say it doesn't matter. It does matter. But you'll see that it doesn't really matter in the end. And the reason why is that the merging process kind of does what it does regardless. So, okay. All right, here we are. So what are we going to do? The first thing we do is we merge the B0s. So we say, okay, the B0 here has to become the child here. Right? And so now we're stuck with two B1s. Put them in order, draw a line. Like this. And then you say, same problem, two B1s, let's merge them. So the good news is that 12 is less than 16, so we merge it down like this. I'm going to try to make it nice and good. And then here, but then you'll say, same problem, we have two B2s. Right? And so now what do you do? Right? Now what we have to do is merge these together. And then you say, well, who's the biggest? 16's the biggest. So who gets merged onto whose children? The answer is 14 becomes one of 14 becomes one of, let's just, since these are latex, steal those. There we go. And then like this. Okay, so that's insert. So how the heck do we do the other operation in a heap? Right? What's the other operation? The other operation is delete, right? So how do we delete? So if you notice, this is how we insert. right? We insert by adding on a B0 with the new data, and then we just merge until we're good, right? So keep in mind here, and let's actually insert another element just so that it's, let's say that we're in this condition, right? So we'll have this B3, and then let's say that we don't have a B2, and we have a B1 and a B0, so let's add those back on, right? So we've inserted another 3 elements. Let's say that here this is, say, 15, and let's say that this is 3, and then this will be 1, okay? Okay, so how do you delete the maximum out of this max heap, right? How do you do it? The answer is like this. So here's a max heap, max binomial heap. How do you delete the max out of this? The answer is you find the max as, I guess I'll put it this way. You find the max as one of the roots of these B trees, B and BI trees, okay? So you notice that, like, you don't necessarily, so there's no preference here. This element could have been 22, right? If 22 were the highest, then we could just delete it and there's no problem. But I don't want it to be the highest, so I'm going to make it 15. Okay. So you find the max as the roots of one of the trees. So you scan through all the roots, and you find what the max is, and then what you do is you do this process. So you basically pull off all of these, right? So this is the max, so it gets, let me write some of this down. So 16 is the max. So we basically are going to, eventually we're going to delete the 16 node. But we don't delete all of its children. So how do we help that? What we're going to do is we're going to merge these two things together. So let me show you how the general process for merge works in a binomial heap. So let's do that now. So here's the general process for merge, okay? So here are 2 binomial heaps, right? So here, once you remove that root node, you notice that the result of doing that is, let's see, where did I put all those B2? B2. The result of doing all of that surgery is that now we have 2 B0s, we have 2 B1s, and we have a B2, right? So this is like the possibilities for what can happen, right? So this is what can happen when you delete a node and try to merge the rest of the structure back in. So same rule applies. Same rule applies. So what we're going to do is this. We're going to say, okay, you cannot have 2 B0s, so we're going to merge them together, right? You're going to merge them together and create another B1. And of course you're going to say, but wait, if you create another B1, then we're even in worse trouble. And the answer is, sort of. We'll fix it. So here we are. So this is the B1 that we're now in the situation where we have this B1, we have this B1, and we have this B1, and then we have an extra B2. So you're like, well, I don't know, this seems worse to me, right? This seems a lot worse. And the answer is not, it's a little worse, but it's not so bad, because here's what we get to do. Here what we're going to do is we're going to pick 2 of these. And you might ask, but which one should I pick? And the answer is that the algorithm usually decides kind of automatically. It doesn't really matter, okay? It actually doesn't really matter which ones you pick. So I'm just going to pick, this one's the result of the addition, so I'm going to leave this one as is. I'm going to merge this one, I'm going to merge these 2 here. I'm going to merge this one with, so I'm going to leave this B1 here, and I'm going to merge these 2 for no particular reason, okay, for no particular reason. I could have done it any other way, all right? So here we go, let's merge. There we are. And so now you're like, okay, I see how this is kind of going, right? Stop rotating. I can't even determine what's straight anymore. I think there, maybe it's close enough. Okay, so point is that we have this B2 and then we have this B2, like this. And so now what we're going to have to do is we're going to have to merge them. And of course I've done it in the wrong order here because 14 is bigger than 12. So when you merge them, you have to do something like this. And there we go. And so now you're like, well, okay, that wasn't so bad. And now we're left with a B1 and a B3, right? So we're left with a B1 and a B3. And so you say, okay, well, that's a binomial heap again, right? It follows the rule. There's no duplicates. There's not two B2s. There's not three B1s. There's just a B1 and a B3. That is a legal state, right? So we're good. We're done. Okay? That's how to do it. So now what if we delete the, what if we do that again? What if we delete the maximum again, right? Let's say we delete the maximum again. Let me show you what happens. Here's the cool thing that happens in this case. So we notice that the maximum is actually part of this B1. So the maximum is going to be 15. And then what happens? We just merge in this B0 with the rest of this structure, to which you're going to tell me, wait a second, but we don't have to do anything because there's already, right? We don't have to do anything extra because this also follows the rules, right? A B0 and a B3 is legal. It's already a binomial heap, so we're happy. Don't do it anymore. Right, so that's the point here. Okay. So, all right. What else am I going to do? So let's delete the max again, right? So if we delete the max again, what we're going to get is this. We are going to get, let's pull this down. 14 is the max. And so now we have to rejoin all of these extra things. And I'm going to stop labeling them because it's pretty obvious what they are, right? If it just has one node, it's a B0. If it has this, it's a B1. If this is B2. So actually, we're not in a terrible situation. Well, unfortunately, I guess we are in a terrible situation because, like, if this 4 wasn't here, right? If this 4 didn't exist, then we'd be fine, right? No more work to do, right? But 4 is here, so what do we do? So the answer is that what you're going to have to do here is you're going to have to merge like this. So you're going to have to say 7 merges onto 4 like this. Please click. There we go. And then these are two B1s, so we have to do another merge. So here's the next merge that you're going to have to do. There we are. And then you're going to have to merge the two B2s because at every point there is an issue. Right? There's too many B1s, there's too many B2s, and there's too many well, there's just one B3. So then we're happy. Okay. So this is the result from this. So now what happens if we delete the max again? Let's just delete the max again and see what happens. So here the maximum is going to be 12. And then here's the cool part. We copy the whole data structure here. There's a B0, there's a B1, there's a B2. This follows the rule. We're good. Completely rule following, maybe? Right? So it's completely rule following in the sense that there's just one B0, there's a B1, there's a B2. We're good. Right? So, yeah. So we're pretty happy here, I think. So here, not a whole lot of work is required. Here, a lot of work was required because once you deleted this, you have the B0 here, which had to be merged. So let me tell you a little secret about all this stuff. Here's the little secret. And that is, you can tell the result purely from the structure and binary addition. So let me show you what I mean by this. Like, let's say that we have a binary thing. So let me just write some binary down. So let me say 1101. Right? So what does that mean? And let me explain what that means, and then we'll plus say, what's some more binary that we can write down? 0111. And you add them together, right? And so remember how you add in binary. And I don't know if maybe you don't know how to add in binary, but I'm about to teach you. So 1 plus 1 is 0, carry a 1, right? That's the rule. That's the rule in binary addition. So 1 plus 1 is equal to 0, carry the 1. So now what we're going to do is we have a 1 sitting up here, right? Technically, like here, carry to 1. And so then we say 1 plus 1 is, again, 0. Carry another 1. 1 plus 1 plus 1, right? 1 plus 1 plus 1 is 3, so actually that's equal to 1. Carry a 1. And then here, what we're going to get is 1 plus 1, which is 0, carry a 1. So, so that's the result, right? That's the result of the binary addition. And so what does all this mean, right? This is just an example. Basically, what this means is that if you read it like this, 1101 means we would have a B3, a B2, no B1, and a B0. And here it means that, and 0111 means that we would have a B2, a B1, B0, no B3. So you know what's going to happen when you merge the two B0s, you're going to get a B1, right? When you merge the two B1s, you're going to get a B2, and then at this point you have a B2 here, you have a B2 here, and then you have a B2 that's the carry, right? And so that's where this 1 plus 1 plus 1 comes in. It's because you have a B2 that's been carried, a B2 here and a B2 here. So when you add those all together, so B2 plus B2 plus B2, you have to pick one of them to leave behind, right? And the other two, so you merge, so you have a B2 plus the merge of a B2 and a B2, which is B3. Right? And then you have two B3s. So then you'll have a merge of a B3 and a B3, which is equal to a B4. So what do we have when we're done, right? So if we notice here, what we have when we're done is we have a single B2 that's left over from the carry. We have a B4 that's left over. We have no B1s left over, right? None left over. And no B's, none, I shouldn't say, yeah, and no B0 ones left over either. So because of that, what we have is we have, if you notice, there's no B0, no B1, so no B0 and B1. There is a B2 because there were 3 of them and one of them didn't get carried. There's no B3 because we merged the two B3s into a B4, so there's no B3. And there is a B4. So if I ever ask you about the structure, right, you know, if I say, what happens when you merge, say, a B4, a B3, and then with, say, a B3, a B2, and a B1, the answer is going to be, well, it's the result when you do something like this, 1, 1, and then 0, 0, 0, because this is 0, 1, 2, 3, 4. And then you add that to 0, 1, 1, 1, 0. You add these together, and what you're going to get here is you're going to get 0, right? Then you're going to get a 1, because 0 plus 1 is 1. Then you'll get another 1. Then remember, 1 plus 1 is 0, carry the 1. And then 1 plus 1 is 0, carry the 1. So what we're going to end up with in the end is, let's align all of that so it looks good. So you'll be able to tell me that basically what we're going to end up with is no B0, a B1 and a B2, so we'll end up with a B1, B2, no B3, no B4, but B5. And so the resulting structure from all of these things are completely the result of binary addition. And that's the reason why I like these things so much. And so if you notice, you can actually merge these data structures. You can merge any two binomial heaps. And the reason why you can merge any two binomial heaps is because binary addition works, right? Because you can add two binary numbers and get another binary number. So you can merge two binary heaps and get another binary heap. And so that's why you can merge these things. Okay, so that's all I really want to talk about today. Maybe tomorrow, or I shouldn't say tomorrow, maybe on Tuesday. So Tuesday, maybe we'll code one. I don't know if I'm brave enough. Maybe we'll code one. Yeah. So and then we'll talk about time complexity. And we'll do some examples, maybe more visualizations. I'll use the web visualizations, and we'll just go through and look at some insertions and deletions. And then we'll code it, and then that's what we'll do. So, yeah. And you see basically here how everything is merge, right? What is delete? Delete is find the maximum node, and then you merge whatever's left once you do that, which is another binomial heap with whatever the current binomial heap is. And so that's one thing. And then insertion is just a merge with a B0. So insert and delete are both merge. Merge is merge. Everything is merge. So again, this is another merge data structure. Mergeable data structure. Mergeable heap. So basically, the only heap that we know currently that isn't mergeable is the array-based heap. The leftist heap, the skew heap, the binomial heap, and then when we get to the Fibonacci heap, they're all going to be mergeable. And so it's just a cool little fact about heaps. So anyway, so that's the point here, and I think that's really all I have for today. I know we didn't do a whole lot of coding. This was all just theory and all just writing this stuff out, but I think my goal here is to take it slow because I know that there was always a lot of confusion about like what all these things are. So hopefully what you should have gotten out of the lecture is that you make a BI plus 1 by taking 2 BIs and then doing this kind of left child process where you shift it down one level and you do this. Oh, right, and the other thing we want to do next time is we want to prove our little induction formula. So there's an inductive proof we can do that shows that the number of nodes in a BI or Bn at level k is n choose k, where n choose k is equal to, if you know the formula, it's n factorial over k factorial times n minus k factorial, right? So it's the combinatorial n choose k. And we will prove that next time because that's I think that's the other reason why I really like these structures. I like the structures for 3 reasons. I think that the binomial structure just as a data structure is actually really beautiful. That's one reason. The other reason is that it maps onto binary addition very nicely. And the other reason is that this inductive proof is really cool. And so for those 3 reasons, I like this data structure. It's not necessarily the best data structure in the universe, and we'll talk about its flaws and its drawbacks and all that stuff, but it is definitely one of the cooler data structures. So, too bad, right? Too bad that you can't do this as your project, because I'm sure everyone would love to implement one of these things. You'll see when I implement it why it's a little bit fuzzy, but yeah. Anyway, we'll implement one and then we'll talk about Fibonacci heaps and all that stuff. So, okay, that's for next time. See ya, everybody.